Welcome to Argo, designing a compact and compressible binary serialization format for GraphQL. Today we're going to do a speed run through the design process for making a GraphQL-specific serialization format. I have a reference implementation and a whole spec written for Argo, so you can even try it out later with like a fully fleshed out version if you're interested. And in this talk, I'm going to assume you already know a lot about GraphQL, and I do plan on going pretty fast. Allow me to introduce myself. I'm Mike Solomon. I'm a software engineer and consultant with a background in distributed systems. I used to work at Twitter, where I was a group tech lead in core services, which is more or less an architect role. And before that, among other things, I built out most of the early version of Twitter's GraphQL API and then helped guide it along for a few years after that. But it's plenty about me. Let's talk about something I think is a lot of fun, serialization formats. Well, I guess before we do that, maybe we should talk about why we care about doing this in the first place. Hopefully you already have some idea of what a data serialization format is, but in short, it's a way to take some data, in our case probably data which fulfills a GraphQL query, turn it into some bits and bytes that we can send over the network and reconstruct on the other side. In GraphQL, that's usually JSON. Why would we want to design a new format? Well, for GraphQL, the main reasons are going to be performance and efficiency. So let's dig into exactly why that is. To understand why we'd want to make a new data serialization format for GraphQL, we have to talk about JSON, which is the default format used by GraphQL implementations everywhere. Did you notice this is the JSON logo? I didn't. But anyway, I also learned it's officially pronounced JSON as of the 2017 standard, but I can't break the habit of calling it JSON, so I'm not going to. Anyway. GraphQL uses JSON. JSON is very convenient. It is convenient because it's simple. It's easy for machines and humans alike to read and write it. It is ubiquitous. There are lots of good tools, even though a text editor is sufficient. There's libraries everywhere for it. It's very easy to debug requests using JSON. It is self-describing. Every JSON message shows the types of the data it contains, and you can often make good guesses about what it represents based on the names of things. And JSON's great. It's probably the best choice for GraphQL's default. However, despite how great it is, it has what I see as three distinct downsides compared to other formats that we could pick. The first is that it's large without compression. When it's not compressed, the textual JSON format often results in messages that are quite large. For example, the names of keys or field names might be repeated hundreds of times. Maybe the string values of enums are repeated many times. And of course, we can compress the whole object, perhaps with gzip or Brotli, but we still have a problem. At some point, we need to parse and read the entire uncompressed response. And that can be slow. We reread the same data many times, and your JSON implementation might recreate tons of redundant objects, maybe applying processing over and over again. If you've ever seen your JSON library show up in a performance profile, you might be running into this. The second problem with JSON is that it's large-ish even with compression. The size of a compressed message is super, super important. In a GraphQL context, this can have a huge impact on the end-to-end latency of a GraphQL query. Tons of users are on unreliable and slow mobile networks, and the bigger the compressed message, the more unreliable and slow their entire experience will be. I've run tons of comparisons of JSON data compressed in various ways, gzip, Brotli, zstandard, LZ4, and I can say conclusively that JSON compresses very well with almost no effort. You just compress it with gzip. You'll often get it down to about 10% of its original size, which is pretty good. And remember, JSON really is a great choice. But I think we should try pushing the performance envelope and see if we can make a format that can do even better. The last big weakness of JSON for GraphQL is that it lacks certain data types. For example, binary data needs to be stuffed into a string, usually by base 64 encoding it, and that can make JSON messages much bigger than they'd otherwise be. Maybe worse, it also means we might need to do some post-processing, like base 64 encoding it, and you have to do that every time. Other than binary data, 64-bit integers aren't elegantly handled on every platform with JSON, so maybe there's something we can do about that as well. But just to summarize, JSON's great, but we can probably improve on its performance and efficiency. So let's do it. Let's design a serialization format. Most great designs start with some concrete goals, so let's write those down so that we're on the same page. But I'm going to really, really simplify what we want today. We're just going to focus on making it compact, which means small when uncompressed, and compressible, which means small after compression. So we'll focus on those two things. We'll also want to keep it relatively simple. And we really care about the end-to-end latency of it, but we'll just focus on these two things. So let's collect some ideas. Most ideas come from observations, and we don't have time today to study GraphQL JSON representations together, but I think it's important that we take a look at what's available to us when we're working in the context of GraphQL to see what problems we might be able to solve and what opportunities exist for us to take advantage of. So here's some JSON that represents a GraphQL response. If you take a moment, you can probably guess quite a bit from its structure. It looks like a response to a query to a social network where you can make posts in multiple languages. And we're looking for opportunities here, especially things to make it more compact and compressible. We should probably be looking for information that's either unnecessary or unnecessarily repeated. And it's actually not that hard to find. You can see that there's some information known from the query, like data, user, and name. We probably came from the GraphQL query that produced this. There's repeated structural information. We see the same name in the field show up multiple times. And there's also repeated values, like the language code for ancient Greek shows up multiple times in this response. Now overall, this is a pretty small GraphQL response, so it's probably not very interesting to make this one much more compact and compressible. But the ideas here will apply to much more interesting and especially larger payloads as well. So let's dig into these a little bit. In GraphQL, responses are responses to queries. This means that both the client and the server are on the same page about what data is being asked for. So here we have a query from the example we saw before, which gives us posts for a user. Since both sides already know quite a bit about what data is being asked for, this is going to be a helpful resource for us to avoid sending information that both sides already know. So don't repeat known structures, probably something we'd like to pursue. We also already have a typed schema along with the query when we're working in GraphQL. I mean, I guess technically the client and server might have slightly different schemas, but they must at least be compatible with each other. But here we can see a little snippet of a schema, just the type definition of a post. There'll be a bunch of other stuff in there too, but again, both the client and the server on each side of the GraphQL request need to know the schema of the GraphQL API in order to use it. And since the schema is mostly information about the types involved, we can probably avoid repeating that information in answer to every query. So don't repeat types. A third idea, we can see here that we have a bunch of different values. In fact, we're going to have lots of values to encode when we're writing almost any JSON or any GraphQL response. And we're going to want to, therefore, make them small. So we'll try to make values small, especially common values. Some things show up a lot more. Zeros, ones, twos probably show up a lot more than 2.5.1 million or whatever. So that's something we might be able to take advantage of as well. We can also get ideas from actual GraphQL libraries and implementations out there. If we look at some of the popular ones like Relay, Apollo Client, or the Guild's GraphQL code generator, we can see that code generation is a popular technique. So that suggests that while we probably don't want to require code generation, we will want to make it easy. So let's take a look at some of the ideas we've collected. And if we look at these all together, to me, they suggest kind of a two-step process. The first step is to collect all the information that both sides know in advance one time. And then second, we'll use that information n times anytime we're fulfilling a request. And that'll help us avoid sending unnecessary information. So let's make this a little bit more concrete. Most of the information known on both sides is going to be type information about what a certain kind of request looks like. So we can call that a type descriptor, which describes the structure of a message. Then we'll be able to use that information many times, especially whenever we're encoding or decoding messages. So let's look at these in more detail as well. We'll start with the two important sources of information we saw before. We have the GraphQL schema and we have the GraphQL query. We'll combine this information into a type descriptor which captures all of the information that we need. This is the distilled essential information we need in order to serialize and deserialize responses to a given GraphQL query. It's also something that we can save or cache or use when debugging or even use in a code generator. Now, instead of looking directly at step 2, we'll look at how values are encoded with JSON. After fulfilling a GraphQL query, we need to send it to the client, so we'll usually have an in-memory value, and then we'll encode it using JSON, and this gives us a serialized value using JSON. Very straightforward. In our step 2, we're going to actually be doing things just slightly differently. We'll start with that same in-memory value, but we'll combine it with a type descriptor, the one that we generated in step 1, and then we can encode it using those, and then we can combine it, you combine those two things and encode it into a serialized value. So of course this is the exact same process as encoding JSON, except that we'll use a type descriptor to help us avoid repeated information. Now, by the way, we could do this 2 different ways. We could build up a whole response and then encode it all at once, or we could encode it piece by piece as we build up the response to the query. Doesn't really matter too much, but we still need to be able to go the other way, so let's take a quick look at that. These steps will usually happen in the client or the app after the server sends a response, back a response to a query. And we'll use that exact same type descriptor. This time we'll use it in combination with the serialized value that the server sent us. And that's enough to decode this back into an in-memory value. This all happens where you'd normally parse your JSON. All right, we still have a long way to go until we've built our entire format, but I think we have a very high-level understanding of our approach with this 2-step system. So let's dig in on the first step, the type descriptors. So each value in a response to a GraphQL query is going to have a type. So let's look at a few of those. We might have a string, maybe some booleans, some integers, floats. We might have an array. Arrays are a little bit more interesting because compound types like arrays actually also have parameters. So this is actually not just an array, it's an array of integers. We also have nullables, such as this nullable boolean. This is a little bit backwards from how GraphQL works normally, where everything's nullable by default, and you can mark it non-null. Here, everything will be non-null by default, and we can mark it nullable. This is just a little bit more convenient to work with in a serialization context. And lastly, we can have objects, such as this object that can potentially have up to 3 fields. We actually have to write down all 3 fields, like my field and a maybe field, and along with their types. And you can see that this instance of this object doesn't have that last maybe field. That's what the little question mark means. That comes up when you're querying for unions and interfaces in GraphQL responses. Sometimes you need to omit fields. So we need a way to represent that at the serialization layer. And it turns out that these 7 are actually all you really need. You can represent all the responses you need to just by combining these types. You might be asking, well, what about enums? Enums can pretty easily be encoded as a string, just like they are in JSON. And unions and interfaces will actually just also use the object representation there. So let's go through an example of actually making one of these type descriptors so we can see how that process of combination works. We always start with a schema. Here we have just like a pretty straightforward small schema for a system where you can post things and do that in different languages, maybe a social network or something. And then let's say we have this query that's asking for all the posts by a certain user. And what we want to do is produce a type descriptor that gives us all the information we need about this so that we can not repeat that on both sides. So we can actually just walk through this field by field and build up the type descriptor as we walk through the query and look up information in the schema. So if we start with the name field in the query, we can look up that same name field in the schema, see that it's a string, and then we can write that out over here to our type descriptor. And we can repeat this process for all the other fields. So for posts, we can look it up in the schema, we see that it's an array, and we can write out that it's an array to our type descriptor. And then we don't have to do this field by field, but you can see we can do it for these other 3 fields, title, languages, and reply count, look up their types in the schema, write them out to the type descriptor. And by the end, we've actually built up this entire type description of the query by combining the query and the schema. And now we have kind of like a common piece of known information on both sides that we can avoid sending over the network. And this is going to help us be more compact. So clients and servers know both the query and the schema. And from these, we'll generate a type descriptor which captures the necessary metadata for serialization and deserialization. So that was kind of our step 1 of our 2-step process. So let's move on to step 2, which is actually using these type descriptors so that we can encode and decode actual messages in response to queries. So here, it'll be a very similar process, but we'll actually start with a type descriptor, and after we've, on the server usually, after we've collected or built up a response in memory to a message, we'll have a value in memory that represents the response we'd like to send back. And here, instead of producing a type descriptor or anything, we're actually going to produce serialized bytes. So when we're encoding, we're actually going to walk through the memory, the value in memory, and look up things in the type descriptor. So here, just like before, we'll start with the name. We'll look that up in the type descriptor, and we can see that the type of this string is string. That doesn't sound very interesting, but it could have been a nullable string or some other slightly different type that we would encode differently. So we look that up, and we can write out some bytes over here into our message. We haven't really talked about this syntax for our serialized bytes, but we will in a little bit. But we can just move on, walking in lockstep from the value in memory, looking up things in the type descriptor, and then writing out some corresponding bytes. So we can do that for post, for title. We can look up that this is in fact a nullable string, which we might encode a little bit differently, write that out to our bytes. Languages, same thing, and reply count is an integer that we write out in yet another format. So that's kind of how the encoding process works. We walk through the value, look things up in the type descriptor, and then write out serialized bytes. Decoding is going to be very similar, except we'll start with the type descriptor, and we'll start with serialized bytes, and this time we're going to try to produce values in memory. This would be like in the client. You need to reconstruct in memory the same thing that the server had. So we'll start with that same name field, but we'll be walking through the type descriptor and then moving through the serialized bytes and producing values in memory. So we can start with this name string. We can look that up in the serialized bytes, knowing that we're reading it as a string, and then we can produce that value in memory. Then we can move on to posts. Again, we're going to kind of move through the bytes and the type descriptor in lockstep and produce another value in memory. Here it will be the beginning of an array. Then for title, we know that we need to read a nullable string. We can get that in memory. And then same for languages and same for reply count. So it's kind of a very similar process in all three cases, whether we're building a type descriptor or using one for encoding and decoding. We just walk through these in synchrony. Now, you might be asking yourself, okay, but what are those bytes? We just looked at a whole bunch of things that got encoded, but how did we actually pick which ones to write or know how to read them? For that, we need to talk about compact binary encodings for GraphQL types and also for their values. So we've seen this before, remember these? We'll actually look at these case by case, and as we do so, our mental model is going to be to write to or read from a stream of bytes. And for syntax, let's talk a little bit about how we can represent that. If this little black box represents a buffer, we'll need to encode values, often integers. So I'll write these in brackets like that, so that would be the integer 20. That way we can still read them, but they'll represent values encoded into bytes in ways we'll talk about in just a moment. Then when we write out strings like this, I won't use brackets since in all the examples it'll just be 1 byte per character, so this would be the string foo, represented by those 3 bytes. And lastly, you can see since we're writing a stream of bytes, we'll be doing a lot of concatenation, so we'll just put the next value right next to it, and that's why everything's kind of just stuffed together. So let's start with integers. Integers are pretty important. They show up quite a bit, and we're actually going to end up reusing them at other places in our binary encoding that we're building up. Now, how do you turn an integer into bits and bytes? Well, there's a lot of ways. This is a pretty well-studied area. We're not going to look into this whole table, I promise. But suffice to say that we can go off and do a whole bunch of research, find out and figure out like what's going to work best for our case. Here, we probably care a lot about how many bytes it takes to store an integer of a given size, and we probably care a lot about ones that are very compact, so we might be interested in a variable length encoding where common values can use fewer bytes and uncommon values can use more bytes, and we just expect that to happen less often. That's going to lead us in the direction of picking something like this. We don't really have time to walk over how we'd make that decision, but let's just observe that in lots of data sets, many integers are close to 0, and a variable length encoding will be more compact on average. So we just researched many binary formats. Now let's use the best one for our goals. For our integers, let's write the integer in a protobuf compatible variable length zigzag encoding for signed integers. Don't have time to talk about what that means, but we could talk about it after. One thing that we care about is this will be between 1 and 10 bytes for 64-bit integers, and it'll only be a single byte for a lot of things that we care a lot about, like the lengths of arrays and strings and a bunch of other things we're going to see in the next couple of slides. Oh yeah, and then we might represent that like that. So let's talk about string. When we write out a string, there's kind of a similar story to integers. String encodings are pretty well studied, and it turns out UTF-8 is a great choice for compact and highly compatible strings. I think that's a great choice for us. So without comparing a bunch of different formats, let's just say we'll write the number of bytes to follow, followed by string data and UTF-8 bytes. And that'll, and when we write that integer, that bytes length, we'll actually use integers encoding that we saw a couple slides ago. So that'll look something like this, just a prefix that says how many bytes are to follow, followed by the UTF-8 bytes. In my experience, many of the total bytes in GraphQL responses come from strings. It's tough to do much about that at this layer, but UTF-8 is about the best we can do. At least maybe we can avoid people making lots of copies or re-encoding their strings. Boolean is very easy. There's only two possibilities, traditionally 0 and 1, so let's just write 0 for false and 1 for true. Again, we'll use integers encoding, which will look something like this, and this is only ever going to use a single byte, so that's pretty small. Booleans are very easy. There's also floats, which we can use for like decimals. Floating point values, again, very well studied. This seems to happen a lot. We should just use other people's careful research. The GraphQL spec for float actually demands signed double precision finite values as specified by IEEE 754. So that makes our decision a little bit easier. We'll just use the IEEE 754 binary 64 format, which always uses 8 bytes, which is fairly compact, but maybe something we could improve on later. That'll look like this. For arrays, such as this array of integers, we really only need to write one thing. We need to write the array of the length so we know how many values are to follow, but the rest can just be encoded as the underlying type. So our strategy here is going to be to write a length, the length of the array, and then concatenate it with the encodings of item 1, item 2, and so forth recursively. So that'll look like this, just a length followed by all the items concatenated together. Generally, this will add a single byte of overhead for each array. Much longer arrays will use a few extra bytes, but will be dominated by the length of the array. And nullables are another case we need to handle, but unlike JSON, we can't actually omit values. So we'll actually need to explicitly mark values as either null or non-null. So we're going to do something a little bit strange. We'll use the number -1 for null and 0 for not null. In this scheme, this still adds a single byte of overhead to each nullable item that's present. There's a trick we can use to avoid this in most cases, and that's actually why that number is negative, but unfortunately we don't have time to fully dig into that today. So that'll look like this, 0, -1 followed by the item if it's present. All right, last one is object. We need to be able to represent objects, just like this we saw before. So most of the time, fields and objects are always present, and we actually don't need to use any bytes to represent them. We can just concatenate the values of all their fields, and because we have that type descriptor from before, we can walk over it and know what value we're reading next. Now, there's one with a question mark there. When you're selecting between unions or interfaces in GraphQL, sometimes fields might be absent. So we are going to, just like in the null case, need to represent whether potentially absent fields are actually absent or actually present. So we're going to use -2 to represent absent fields, and we'll write 0 before potentially absent fields when they're present. This is almost exactly like the nullable case, so that we can represent that difference. And again, we can later use a similar trick to avoid that overhead, even though we don't have too much time to talk about that today. So is it compact yet? Sorta. The individual values have compact representations. We just went through all 7 of them, and that makes a big difference. But there are still some tricks that we can apply. So let's talk about that a little bit. One problem we still have in this format so far is that binary data is big when we stuff it into strings, which is currently our best option, and the best option we have in JSON. You have to base 64 or even worse, Unicode escape it, and that's going to result in a very big string. But fortunately, since we're already designing a new type, we can easily add a new type. So let's add a bytes type, and that's going to be very simple. We're just going to write the number of bytes to follow, followed by the bytes. That'll look like this. In the scheme, that does leave us with a communication problem where both the client and the server still need to be on the same page about how this value is encoded. So we'll probably need to do something like put a directive in the schema that tells us how a custom scalar is encoded. So we could use a directive like Argo codec, say that we're using the bytes codec for the image preview custom scalar, and that would keep both sides on the same page so that we don't need to try to communicate this information out of band. Another opportunity we have is that many values are repeated, such as the language code for ancient Greek again comes up multiple times. Over the internet, if we're using compression like gzip, then there's a good chance that a lot of this will compress away. But as we discussed before, we still have to pay the serialization and deserialization costs for each value. So we might be able to improve on this by deduplicating repeated values. Let's work through a pretty detailed example of encoding an interesting payload, and at the same time, we'll see how we can deduplicate repeated values. So this will be both enlightening and maybe a little bit tedious. We're going to start with the input of just these 2 objects in an array, and we're going to write out a buffer of encoded bytes there at the bottom. Let's start with the fact that we're writing an array, and as we talked about in the encoding before, we need to write its length. So we'll write 2 for the length. We can then move on to the first object. Objects don't actually have an explicit representation in bytes, so we'll just jump straight to the first field, which is ships. And now this is a value that we might be interested in actually deduplicating. So to do that, let's introduce a deduplication table. We'll write out an ID column along with a column for every type that we might care to deduplicate. Here it'll just be the string and the language enum. And we'll start numbering at -3. You might notice we're continuing that negative numbering scheme that we started with the nullable and potentially absent types. And here let's put the ships entry in there in the deduplication table. So we'll just take note of that for later, and we'll actually write out the value to our buffer. First we write its length, which is 5, and then we write the UTF-8 bytes, which is just ships like that. And we can finally move on to languages. Languages is just another array, so we'll write its length, which is 2, and then we can move inside to encode this language enum value, which we're going to write as a string. We might want to deduplicate this, so let's write it into our deduplication table. We can actually share the same ID as for ships. They don't collide because we know they're different types, so we'll write en into that deduplication table, and then we'll actually write the serialized bytes into the buffer. So first we write its length, which is 2, and then the string, the UTF-8 bytes as well. Then we can move on to ancient Greek. And here we're going to need to introduce a new ID, and we can put that into our deduplication table at -4. And then we can write that to our encoded bytes. Its length is 3, and the UTF-8 bytes are GRC. Now we can move on to boats, also not very interesting. We'll just write we write it to the deduplication table, and then we write its bytes out, 5 in boats. And then we have to write the languages array, which is 2. And finally, we get to something that maybe is a little bit more interesting. We get to en, and this is actually a value that we've seen before. We can tell because we can see it in our deduplication table for this type. So instead of re-serializing this, we're going to look up its ID, which is -3, and we'll instead write that to our encoded bytes. So we'll just write a -3. In this case, this is going to save all of 2 bytes. Not all that interesting, but if this is a bigger string or if it showed up hundreds or thousands of times, it could actually start getting interesting. Now we'll see the same thing happen with GRC. We'll see that that's in our language column of our deduplication table, and we'll write out a -4 instead. So we're able to deduplicate values. So is it compact yet? Yeah, it is. It's pretty compact. We have compact values. We have low overhead binary values. We have deduplication of values. In the actual spec, there are a handful of other tricks as well. We don't really have time to dig into them, but we're going to end up with pretty small messages even before applying compression at this point. So is it compressible yet? Sorta. JSON's already very compressible, and what we've developed so far will definitely compress down quite a bit. But we haven't actually done very much explicitly to make it unusually compressible. So let's do that by introducing a compressible layout. And for a little insight here, we might make the observation that compression algorithms work best when given long sequences of similar data. We might also notice that values of the same type tend to be similar. So this kind of leads to the idea that we could group values together by type into blocks, and this would actually assist whatever compression algorithm we use into squeezing them down into less space. So for example, we just built up this entire serialized value using inline values, and you can see we intermix integers and UTF-8 bytes. Instead, what we might want to do is put values in blocks. So we could start with all the string values together, then we could write all of the language codes together, and then we can write all of those integers together. And in practice, this does compress better. So let's walk through how this would actually work. We won't go in quite as laborious a detail as we did last time, but we'll look at the same example. It's the same encoding example as before, but we're going to modify it to write out contiguous blocks of values. And you can see those are the encoded bytes at the bottom from before. That's what we're going to replace. But we might notice that we actually already basically have these blocks put together for us in the deduplication table. In the string column, we have all of our string values. In the language column, we have all of our language values. So it's actually going to be pretty straightforward to put these all together and assist the compression algorithm later. So instead of walking through it again, we'll just say that we walk through the same algorithm we did in laborious detail before, but every time we write something to the deduplication table, we won't write it to our encoded bytes. We'll just skip it. So that'll give us something like this, or maybe we write the lengths to the encoded bytes. That'll give us a block of integers like this, and then we can actually go through all the columns in our deduplication table one by one in the order they showed up and create blocks from them. So if we focus on string, we can concatenate all of those values together and prefix it with the length of the entire block. We end up with 10 ships boats, and we can kind of slide over our encoded bytes and stuff this onto the front. And now we have a block of all the string values at the beginning that should compress better than it would if they were interleaved. Then we can do the same thing for the language values. We'll put them together into a block, prefix them with their length, and kind of slide that into the front. And what we end up with at the end is a very similar value, but in a different order that will compress better. That's pretty neat. So, results. Revisiting our goals. Is it compact? Yeah, it is compact. Based on my testing, without compression, Argo reduces message sizes by about 50 to 80% versus corresponding JSON. Now, results may be much better or much worse depending on your data. All this stuff is going to be very, very dependent on your data. But that's quite the reduction in size. And remember, you do need to actually read through all these bytes at some point, usually parsing, and you might be able to squeeze a little extra performance out of it there, even if you're compressing, which you usually will be. Which makes us wonder, is it compressible? Yes, it is. It's unusually compressible. After compression, Argo reduces message sizes by about 5 to 15% versus corresponding compressed JSON. Again, your results may be much better or much worse depending on what they actually are. But that's probably the range we're talking about. If you're looking for performance opportunities, that's roughly the size we're talking about. All right, so real talk. We could go deeper. There's a bunch of stuff we could talk about here, like variable length float encodings, or input types, or mutation types, or benchmarks, tools, implementations, but we're already over time and have no time for that. So I could talk about it all day. So if you want to, come find me, and we will until you're tired of it. But a few key takeaways. JSON is actually great for most use cases. Most people have no reason to ever pursue any of this, and I think that's actually awesome. If you are looking for kind of a middle ground, just more of a drop-in replacement, CBOR is a pretty good drop-in upgrade. That will get you more compact values and more widely available libraries. You can just look up what that is. We didn't talk about it at all today. I found that compressed values are not very much smaller, but they are definitely more compact. So maybe you can get some value there. If you want to go all in on a custom binary serialization format, Argo is a lot more complex. I mean, we just walked through some of the complexity. Most of the complexity you'll actually run into is around the ecosystem. There's not a mature set of libraries. Debugging will be more difficult because there's not tools to debug it and that sort of thing. But it might pay off if you really need it. So if you're looking for every last ounce of performance, maybe this is something you could pursue without actually asking most engineers to do anything at all. If you're interested in the spec or in any of the, or the reference implementation or any of that, you can find it at this URL. My name's Mike Solomon. Here's some ways you can contact me if you care to. And thanks very much for coming. Appreciate it.